University of Iran, and as you know, the manifesto of the DigitalFutures education should be free and a human right and not the privilege of the wealthy. Actually, in this workshop, occupant well-being through performance simulation and optimization, you will learn how to create a research framework and design adaptive facade with professional level simulation and optimization techniques. Actually, as you see in the picture, I mentioned, excuse me, yes.
Sorry to interrupt you, but the presentation you are sharing is not on the presentation mode. Like we see also the next slide view.
Excuse me, check it right now.
Yeah, now it's okay.
And now, what about now?
Yeah, now it's okay.
And also, thank you. And also, we are so thrilled to have Professor Mohamed Hamdy, who is a full professor at NTNU Department of Civil and Environmental Engineering with 80 years of experience in building performance simulation and optimization. He is an expert in building simulation, building automation systems, multi-objective optimization, life cycle cost analysis, and building information modeling. He also has a T2 peer-reviewed publications. Additionally, he supervises PhD theses and serves as an associate editor for Frontiers in Built Environment. Thank you so much for joining us, Professor Hamdy. We are so thrilled to have you in this workshop. Actually, thank you so much for accepting our invitation, and we are looking forward to hear from you.
Yes, hello. Good morning, everyone. So today we're going to have our presentation is about building performance resilience. So first, I would like to share my screen. So, I think you need to enable me to share my slides.
Yeah, of course, yeah. Now, could you please try again?
Okay. Yes. So now I'm sharing my screen. Do you?
Yes, yes, of course.
Yeah, okay, good. So it's in presentation mode or?
No, it's just a slide. We can see a slide.
Okay.
You can extend the slide if you would like.
Yeah, is it okay like now?
Yes, okay.
Okay. But because I need also to go through the slides, so, so that's why.
Yes, of course. Oh, feel free.
Okay, so first, yeah. Okay, so let's start for now our lecture. So first of all, I would like to thank you all for inviting me to give this lecture and session in your workshop. So today we're going to talk about resilience of building performance, and there is two main points in resilience, because if we ask everyone here in the session what is resilience, it's usually we get different answers. So that's why it's very important when we talk about resilience. It's a very hot topic nowadays, but still need to be defined well. And these terminologies need to have the same definition for all people in this field. Otherwise, everyone talking about resilience from his opinion, and then we cannot get agreement, and we are not have the same floor talking from the same floor. So today it's very important to talk about resilience of building performance. And when we talk about performance, we will mention different things, including two interesting things about thermal comfort and visual, that is one of goals of this session. It's important to know how to quantify, and here we will present how to quantify using simulation, or in specifically building performance simulation. And also we will see how to improve smartness in order to improve resilience. This is me, I'm Mohamed Hamdy, as introduced, full professor in Norwegian University of Science and Technology. It's a quick brief about also the history of my career. So I'm originally Egyptian, and then I grew up in United Arab Emirates, and then PhD in Finland. Then I was in Netherlands. So he was one of the presenter here. He was my colleague in Netherlands. And then I moved to Germany, then for now, or 6 years in Norway. I also participated in international groups like IE Annex 80 and Annex 82 about resilience and about flexibility. There is also I was like a business developer in 2 companies, Lavalone and MetaBuild. Here is, in general, the main goal is we working here in Europe mostly to achieve European goals. And based on European Council, we have different targets and missions to work on. So in the EU missions, there is 5 missions, as you can see here, like adaptive climate challenge, which is one of big aim here in this session. So we are in line with this mission. And then there is another 2 sessions about topics not relevant to built environment. And the 4th mission is about neutral climate cities. And they have like a goal to achieve 100 neutral climate smart cities by 2030. It's a very challenging point, but luckily that Trondheim, which is my city in Norway, it's one of these 100 to be neutral climate smart city by 2030. So that's why we're working hardly on that. But at the same time, we also working on adaptive climate challenge. And here resilience is a topic. So we have target to have 150 European region and communities to become climate resilient by also 2030. And that's why it's very important to have agreement on what is resilient. Generally speaking, in Europe, we're talking about climate resilience, flexibility, and also like circular building, about reusability and reuse of materials. So this figure shows different main points we are working on here. Yeah, I try to move slides for now. So. Okay, so actually I have issue to go to next slide from my side.
Yeah, close your sharing and then.
Does it go now? Does it go?
No. Yes, of course.
Do you see my slides now, right?
Now it's a slide 4.
Okay, and now slide 5. Okay, good. So here is about these annexes, which is IEA, International Energy Agency, EPC Annex. So there is 2 different annexes we are working on. Annex 82 about energy flexibility and Annex 80 about energy resilience. And for now, we have a new annex. It's established recently, is about energy resilience of building in remote areas. And this will come a new annex called Annex 93. So this one is established recently by these universities. You can see it in the slide. Meanwhile, also at NTNU, we have 2 big projects talking about neutral climate and zero emission buildings. It's called Zero Energy Building. This is one of its 8-year national project with more than 52 partners from industry and from research. And also before this project, we had a project called ZEP, Zero Energy Building, and now we have Zero Energy Neighborhood. So we work on larger scale. Let's go to the topic and the resilience of building performance. So if we talk about performance, we have thermal performance, and we have indoor environment quality, and we have productivity performance, and we have energy performance and cost performance. Maybe as we all know that it's very important to have thermal comfort, not only to feel satisfied in our buildings, but also it has very important impact on economics, because it has a direct relation with productivity inside office buildings, and also in residential building. If you don't sleep well, you will not work well. In education, you will not get lessons if you don't breathe well. So it's a very important and connected to indoor air quality. And it's also connected to diseases, and this very obvious in when we have the pandemic about COVID-19. It's very important to care about ventilation of buildings and also thermal comfort, because temperature has a very direct relation with viruses and bacteria come in indoors and how fast they can grow. So if we talk today about resilience, we will focus on energy performance, and we're talking also about thermal comfort. This is the main topics. So if we come here is about resilience design is a new thinking, because we go from fail-safe design to safe to fail design. So usually we create our buildings not to fail. So this is how traditionally a designer think about the problem. But actually, the truth is that we should be able to accept failure, but to be resilient, it means we are able to not drop very much, and also we can recover fastly. So, and this will come in detail in the coming slides when we talk about the definition of resilience. But as a concept of resilience, it means, okay, to fail, but you can come back. And the resilience here, it can be defined on you as a person, or in industry, or in buildings. So depends on what we are talking about, we will define resilience. So if we talk about people and we describe someone as a resilient person, it means even there is a lot of hard times in life, but you can recover. First of all, you can resist somehow, and then you can recover. But also you need to get to learn from that and to be smarter, to learn for next stresses, to adapt to new stresses and deal more smartly with it. The same for building. We will talk about this cycle of resilience. Before we go to this cycle, here, when we talk about resilience, we have event or disruption happened that make degradation in the performance. And usually when we have some events or disruption events, we can classify them about probability and impact. Some events are simple, and so they don't have big impact. So the impact is low. And the probability is low also. It means it's a very rarely to be happened. So we have four like boxes here, or slots. And when we talk about resilience, we talk about events which has low probability. It's not often to happen. But if it happened, it has high impact. So if you are able to deal with this situation, you are resilient. So when we talk about resilience, we talk about low probability and high impact. So we will see, because traditionally in design, we work on high probability things because it's most often to be happened. But resilience, it means it's low probability, but have a high impact. That's very important also to prepare for that because of climate change and big events, disruption events. So in order to go more deep in the concept of resilience, we would like to say resilience has different attributes. So one of the attributes about the efficiency, robustness, and sourcefulness, and randomness, and flexibility and adaptation. So each one of these definitions, if we ask ourselves what's efficiency, what's robustness, what's flexibility, and so on, many people are a bit also confused. So we need to know what is the definition of each one and what, because sometimes there is trade-off between these attributes. But in order to be resilient, you have to behave good on all these regards, to be efficient, robust, and also resourcefulness, and so on. Okay, so in order to be very specified and have a common definition for all of us, we need to make things are very well defined and simple. So we came with this. First of all, when we talk about resilience, we have to ask ourselves about four main questions. The first question is resilience of what? So what we are talking about, what is the boundaries of what we are talking about? Definitely here we talk about building. So we talk about the building. So if we say resilience of what, the answer is building. But it's not enough to say just the building, because after we say a building, we need to say what is the boundary of the building and what is included inside the building. So do we mean only the building? It means the rooms? Or are we talking about the building and energy system inside the building? Or the building and connection with electric grid, for example, or different power supply and renewables. So we have to put a boundary about what we are talking about. So here to answer resilience of what, it's important to pay attention to that. Because based on your answer, the work will be. Then resilience to what? So we're talking about building. Here we have to be resilience in terms of, for example, daylight, or about lighting in general, or about visual comfort in general, or about thermal comfort. So here we talk about resilience to what? So what we are talking about. Sorry, this is not to what, but this is based on what. Sorry for this. When we talk about resilience to what, it means that disruption event. So maybe there is a lot of events that happened, like heat wave or cold wave or electric power cut in electricity. So resilience to what? You cannot be resilient to everything, okay? Like persons, you can be resilient to some stresses, but you are not resilient to other kinds of stresses. And resilience in what state? It means also there is different stages to be resilient, to be resistance first, and then degradation, and you have to be absorb this degradation or in performance. And there is other two phases. So here is about the state or phases of resilience, and this is of what is the boundary to what about disruption event, and based on what it means mainly key performance indicator you are talking about. Okay, so here is the major challenge is to protect buildings performance against upcoming challenges. And let's go directly and see here as about resilience of what. So resilience of what we can talk about single zone, system, or building, or neighborhood, or larger scale, as we mentioned. So building can include different things here. Resilience to what? It's a very, very important. So in order to what? We talking about different events. So these events, it's called disruption events. So it's something attack the building. So in order to classify this disruption, we can classify to be natural disruptions or technical disruption. Natural disruption, it can be meteorological, related to weather, or hydrological, related to floods for water in general, and or geophysics, and also about meteorological, and also like biological, like diseases and pandemics. Technical, it can be related to general failure, like in the power failure, or failure in HVAC system or systems that make comfort to be happened. So this is a general classification. It came from this literature, and there was a PhD by Shabnam. She is also like Iranian. So I was very proud of her work with me, actually. I will come to her thesis also in one of coming slides. So here is about resilience design. Resilience to what? We have different events, as we mentioned. And if we talk about, we focused recently on work on resilience to cold events and also power grid electricity cuts. So this is just from statistics, how much these can be severe events and make big problems. Let's go to resilience on in what stage. So as maybe you can see here in this figure, the phases of to be resilient. So here we talk about building performance level, and on this on y-axis, and on x-axis we have the time. So in the beginning we have initial state. That means everything is okay. Let's talk about this Pn is the set point temperature, let's say 21 to have it in cold climate countries. And it's still 21 in initial state, no disruption happened. But when disruption starts here at time T1, we expect the performance or temperature. In this case, performance can be defined in different way, as we mentioned, different key performance indicator. In this case, we talk about temperature. Temperature will drop down. So here disruption, when during the disruption event, this is one of phases. And then building will start to recover when disruption disappeared. So this we call it recovery phase. And then final state, we should come back to the initial state, but the system are able to learn here and get some messages after full recovery of building. So if we go further here, we can see also about resilience assessment, and we have investigated different approaches to quantify resilience, and they say resilience of what? So we should go to metrics or key performance indicator. So there is different key performance indicator we have found, but there is shortage in most of them because they don't cover the 4 stages. So that's why we went and developed our key performance indicator based on temperature. In order to make this development, we wanted to have some criteria. Let's say we have this resilience metric should help the decision maker and able to make benchmarking. And also resilience metric shouldn't only capture the performance during the disruption event, but also after disruption event. So we started to put some points for us to think how we going to define a good metric for resilience. Here, this was mainly somehow like research questions and goal for a PhD by Shabnam, which I mentioned. And that was the PhD thesis toward resilience building performance definition, framework, and metric is made by her. And what is coming as output here is we started to define building resilience to prepare for the event and also to absorb in second phase and adapt and recover. So if we are able to do all that we will be resilient, but we want to quantify that. This is the main paper of the PhD thesis with the title also Thermal Resilience Buildings, How to Quantify a Novel Benchmarking Framework for Labeling Metrics. So also we develop a metric to quantify resilience. By the way, this is a session for discussion, so feel free if there is something you want to stop me, please do it. Okay, so here is again definition about these stages, about initial phase 1, phase 2, phase 3. And we figured out we have to define different level of comfort during the event, because we cannot say there is degradation and that's it, but we have to define this degradation in performance, is it acceptable level or habitable level or unhabitable level, okay? And in order to quantify resilience, of course, if degradation happened fast, it means this area will be large. And then if you stay more and if you go, more degradation happened, it means you are in more bad situation. And here is unhabitable level or situation. So if you spend longer time here is too bad. Here is also bad. Here is less bad, let's say. So we have to care about how severe is the degradation happened and how fast it happened and how much you stay in each state. So that's why these stages can be different from application to another application. If we talk about building with people inside, this will be the thermal comfort criteria, different level of thermal comfort criteria. If we talk about refrigerator and like supermarket, it will be different way because we have to care about also food inside the supermarket and so on. So it depends. This, we focus on residential building and to say the phase of event and hazard of event and exposure time of event. Here, this figure is more clear or to the point, summarizing what we were talking about. So here we applied for a temperature. So the key performance indicator become to be temperature, T set point, T habitable and unhabitable level, and this is a minimum happened based on disruption event. So here, initial state, disruption happened. When disruption happened, degradation happened. There is segments S1 and S2. S1, it means the first period of time you stay in this acceptable level. S2 is the second phase of time, exposure time is longer, so you stayed more. So it has more penalty to be in this level. So on in a habitable level and unhabitable level. So of course, if you are in segment S6, it will be very bad situation. So we give like a penalty for how much you stay in each segment, and also if you are in degradation or in your recovery phase. Because when you are in recovery phase, your body and your people inside the places, they realize the situation is recovering, so they have more hope to everything to be happy. So that's why the bad situation here become less significant, and influence of it is less than during degradation, where people don't know to where they are going and when it will stop. So this table shows the penalty of the phases and the hazard and also exposure time. So in order to define the temperature limits, it's also challenging because when we have a building, it's multi-zone building. It's not only single zone. So if you have a like living room, the comfort level will be different than in bathroom or in bedrooms. Other thing, thermal comfort, if we're talking about many buildings, like let's say have operable windows, it means window can be opened. In buildings with operable windows, for example, or a lot of adaptation, comfort is not fixed. So we cannot say temperature of to be felt comfort is 21. No, it depends on running mean outdoor temperature. For people, like for audience who knows about adaptive thermal comfort level, this figure is about adaptive thermal comfort level, which shows on x-axis mean running temperature, which is temperature of the moment and also temperature of some points from previous hours or previous days, depends. And here depend on the history of temperature, the acceptable temperature will be. And also, so that's why the set point here is curve, like, or it's line. So this comfort can be different from time to time. So also the set point here, we don't expect to be fixed. This set point is depend on what you have as a threshold in your adaptive thermal comfort level. So in this figure, it shows fixed, but in reality, in the equation is not fixed. The other thing is that at this adaptive thermal comfort level is different from zone to zone. So we have multi-zone. So here we have unmet temperature limit. We have defined this weighted unmet thermal performance to quantify. And we used indoor overheating degree in order to quantify the overheating or undercooling, let's say, whatever situation we're talking about at each zone. and also giving the time of people spent at each zone. So this work, by the way, indoor overheating degree, it was developed like maybe more than 8 years ago. It was in Netherlands, in Eindhoven University. I know there was a lecturer from there, so I was also there, and it's developed at the time when I was in Netherlands. And here in Norway, we developed this resilience indicator, including indoor overheating degree and under cooling degree, giving all these weight factors. Not to expand more, I think the idea here is clear for how to quantify resilience, and we take it to have indicator or label to say, okay, if this resilience climate indicator is from this range to this range, we are class A, it's like thermocomfort level, or class B and C and E, depends on how big the quantification of resilience. But now we succeeded to quantify resilience and make benchmarking for different type of buildings. One thing which I also forgot to mention here is about when you make these tests, we create these tests using simulation tools. So everything is under control. In order to make benchmarking for buildings, you have to make the same assumption for all of them in order to benchmark the performance. So you have to design a framework, which is fixed framework, to test all buildings at the same situation. So here, this is what we call it a framework. So we decide to leave the building running for a while, and it's defined in the work. And then you make power cut for 6 days, and then you stop the disruption, whatever power cut or other kind of disruption, and then you leave it to recover and go to the set point. Its time here is not defined because it depends on behavior of the building. And we have a future work to work on how the building can become smarter and learn for next cycles. So this is another work is done in collaboration with Finland, Aalto University, and VTT in Finland. Okay, so we published this work on, here is a framework I talked about. It's 1 day in initial state, and then 4 days power failure or event happened, whatever it is, and then 4 days in phase 2, and this can be and then 1 day for initial state. So this to be fixed framework to make benchmarking if we want to make benchmark. Here, this is a result of this building performance. This temperature here is clear, and the level of acceptable, habitable level and unhabitable level is also clear. So this is when temperature drop, the temperature will drop when event happened. And then building also temperature will recover when event is ended, like power cut is ended. But here we did this study also for this in order to improve, to test how to improve. So if we have a battery or if we have solar collectors as additional power supply, how the behavior of degradation will be fast and how much it will be severe. So it will go down or not. So this one is with battery, for example. Sorry, this figure is this figure blue is passive, and this one is passive with battery, and this is only passive, and this is standard and standard with battery. So the first one is a standard house. The second figure is for passive house, and then if you have dots. This is for with battery. So you see the battery here make degradation less, and passive house make degradation less. So the best if you have passive house and battery. But here, maybe this is logic, but it was important to quantify and see how much, because you cannot make benchmarking without quantifying. So I see the time now is also running. So I will mention here, this is about improving with PV. The previous one, it was improving by battery, improving by PV for also passive house and not passive house. Here, when we talk about model predictive also control, how this can improve the performance. This study shows also like comparison between standard house, standard with battery, standard with PV, passive with battery, passive and PV. And then this is labels of resilience can be quantified for each one. So this is how we can quantify the improvement of energy performance resilience by using different technologies. The same work happened, the all work I showed to you, it was for power cut and degradation is drop in temperature set point or temperature in rooms. Here, then we collaborated also with USA in University of New York College, and we did the same approach but for overheating. And the paper title is Impact of Building Retrofitting on Thermal Resilience against Power Cut, a case study with air-conditioned house. So now we talk about hot climate. Previously, we were talking about cold climate. And the study is also this, the same indicator is examined for hot climate with using the same approach. So here we see temperature go up, instead is go down like previous one. And here also we made like waiting for each phase of degradation. And this is the main results. And this is also the benchmarking and for building retrofitting solution, different solution to quantify how the label of resilience will be for each case. That was the conclusion for now, I think, because it's like half an hour presentation. So I would like to thank you, and I'm very happy to receive your question and make discussion as you wish.
Thank you so much, Professor Hamdy, for your fruitful presentation. And everybody, if you have any question, please put your comment in chat box or raise your hand and open your camera.
Thank you so much, Professor Hamdy and Zahra, for creating this meeting. I didn't know I can ask a question.
Yes.
Yeah.
Yes, sure.
In the first, I really thank you for your great presentation because it's really aligned with my topic in the PhDs. But my first question is about how do you define the cold snap? Because for the heat waves, we're using the Quincy method, but for cold snap, we haven't any, I can't find any resources to define, okay, how can found the cold snap during the futures.
Yeah, but to be honest, I know this channel because there is a less literature in this topic. Yeah. So I know that. But in this work, it was the main idea is to focus on the framework itself, how to create a framework to make assessment. So we have even some assumptions or what we got what's available in literature and have been used to create the framework.
Okay.
And now we have this new annex. It's called the Annex for Remote Area and Cold Climate Countries. It's 93. This topic you're talking about, it will be one chapter inside it. So because it needs further research. And this is good that you already have a PhD on that topic. Yes.
Yeah, exactly. And I didn't know if Fabio was talking to you for some times.
Yeah, sure.
Yeah. But in the slide 24, you're talking about some indicator WUMTP, but for calculate these indicators, you have to conduct the analysis in the which time period, for example, for the whole of the years, or just a specific time of the cold snap, for example, 7 days before, after, and duration of the cold snap.
Yeah. Actually, for this, we made it fixed, like for the coldest period of this country. So, and we recommend, for example, because here we talk about power cut in cold climate countries, and we're talking about heating system, right?
Yeah.
So, in this case, we made some recommendation is to make it fixed, like 4 days, as I showed here, like 1 day, 4 days, 4 days, and 1 day. When we do that, we do it during the coldest period of the year in this country. So each country go to what is the coldest period, and then they can make.
So just a short time analysis, not the whole of the TMY and yearly analysis.
No, this is short. Yes, it's like, you know, when we make design condition, it's like that. So we also fix the condition to make the test, because otherwise it will not be a test. It will be tested for, but this is like testing for labeling. So it should be standard.
Yeah.
So for this is the reason why we went to this direction, and to make benchmarking for different type of buildings.
And for this type of the analysis is based on the air temperature inside the building, duration, the power outage, and cold snap. And you're doing the some post-processing to drawing and calculate this type, it's right?
Yes, there is post-processing for sure.
Yeah. And because I searched a lot and reading all the articles by you and also the Shabnam Homai, but I can't find of any coding and anything to explain a specific this topic. So how we can calculate this indicator for our buildings.
But it's okay. So maybe we can talk further about this topic if you wish, but I think it's also like simple, because first of all, you need to define what is the set point or temperature thresholds, different one. And in order to calculate it, you have to calculate the running mean outdoor temperature to see what is the adaptive limit.
Yeah, I do it this part.
Yeah, and then you apply it for each time step. So is it still challenging for you to do it like that?
Yeah.
You're searching for the code itself, right?
Yeah, exactly. And that's so in the Annex 93, you're working specific on the cold snap part to define that. It's right?
Yeah, it's going to be part. Yeah.
Okay. Thank you so much.
Yeah, you're welcome. So I'm open for questions in general regarding to this topic and the building performance simulation in general. Yes.
From my side now, because I'm working in this major and doing some framework into doing parametric simulation ways.
Perfect. So you do your PhD in Iran or somewhere else?
No. I'm working with Fabio in the Politecnico di Torino.
Fabio, yes.
Fabio Favoino, yeah. And working on the advanced building envelope system to mitigate and constrain the climate. I focus on the heat waves, but to doing the thermal resilience, improve it. And it's very similar to Annex 18 work.
For Annex 82, right?
Annex 18, I think, was the Shadi.
80 only.
18.
Yeah. Only 80, yes.
Yeah.
For resilient cooling, yes.
Exactly.
This where Shabnam was there as well. But
yeah, exactly. I talked with Shabnam several times, and she really helped me.
Yeah. And I showed you also maybe this other work with California College.
Yes, I read in that. And you creating the reverse ways, because in the previous one you dropped the air temperature, but now it's about our heating degree.
And I assume also Cheyenne is Iranian guy as well. Yeah.
I think this topic is all the Iranians work in this major. Also the Kavan Javanrodi and Wahidnik in the Lund University creating some framework for the future weather data.
Okay, good.
Yeah. Thank you.
And my regards to Fabio, because I didn't see him for a year. So
now he's in the Toronto. Is presented our first report about the thermal framework of the analysis, the thermal resilience in the buildings.
Yes, sounds very interesting.
Yeah, thank you so much.
Thank you so much for conversation. Actually, there's a question from Fatima Mohseni, and she asked, could you please explain more about the solutions to improve the building resilience in the failure examples you said?
It's about improving resilience. So here in this study, we examined actually only 2 solutions, or 3 actually. Let's see. Here is about the building to be, again, here we talk about resilience in cold climate countries and power grid, because again, as I mentioned, resilience can be defined in different ways. So depend on which resilience we're talking about, the solution will be. So here, because we're talking about degradation of temperature or temperature drop in buildings, so we had a standard house as a reference and the passive house, because when you have more insulation, of course, degradation is expected to be less. So passive house, it means more insulation and less ventilation also is used. This can improve resilience, definitely. It was expected, but here we wanted to quantify. Power, when we have energy storage in battery, also you have this battery help you to survive, or this, for example, horizontal line is, and this one again, it's mainly because when you have a battery, then you can survive before degradation happens that fast. And so this solution is about building envelope. Here we didn't talk about adaptive building envelope. I know this workshop, it was talking about that. It's very important to also to examine different solutions about adaptive facade, how it can help. But here we talk about fixed, not adaptive, and it's just passive. And the battery and also photovoltaic with PP. So all of them can extend, depends on you have power to be used even there is power failure, or you have extra power from solar, but of course not all of them can be utilized immediately. So that's why you cannot calculate it simply and say, okay, I will generate this power and it will let me survive that long. No, because not all of power generation can be utilized at the same time, especially if you don't have a buffering or a battery, for example. So here we examine these solutions, but actually there is more, depends on which kind of key performance indicator is used. I hope this answers somehow the question. It's a question from Fatima.
Yes, thank you.
Okay.
So then some of the solutions could result in having an adaptive building.
Yeah.
Okay. Thank you.
Yeah, you are welcome. But maybe it worth also to mention here is when you work on resilience, some solution can improve resilience, but some solution also is not good from energy efficiency. Not this one, but this one, it was good for both. But just generally speaking, not solution you can propose, it can be good for resilience, but maybe it's not the best for energy consumption or cost effectiveness, or also flexibility, energy flexibility. This in coming work, we can show also the trade-off between flexibility and resilience and energy efficiency. We have another work, it's not presented here already, but we working on another one to deliver the message more further.
So
Yes.
So at the end, this study of resilience is to help buildings to be like, it's to help the thermal comfort, not specifically the consumption, right? You're saying this? Or?
Yeah, that's what I tried to say here. Actually, the main goal, it was not only to improve, but in order to quantify it. Because once you quantify, you can improve. So we did the study and create the framework to quantify resilience. And then we studied solution for improving the resilience. And direct answer to your question, or yes, we were focusing on resilience and how to be quantified, not about energy efficiency.
Okay, thank you.
Yeah, you're welcome. Because it's as a plan also, like this kind of indicator to quantify energy resilience, it can be in a standard new regulation. So that was proposed by IE Annex 80 in resilient cooling, for example, is to make recommendation for countries to add a new indicator to be in when you have certificate for building, you have certificate for energy efficiency, and also you have certificate for energy resilience. because resilience become very important topic because of power cut, lack of resources sometimes, and also disruption event and energy securities in many countries and many regions. And this will be focusing more in remote areas in this new annex I mentioned that's called Annex 93, because in remote areas, the topic of resilience is even much more important because resources are not very easy to be available and you cannot secure to deliver it in time. So, but in general, we put this as a new key performance indicator to be in the certificates of buildings.
Yes, thank you. And then, like mostly the materials in the building could affect the changing of different resilience in different buildings, or?
Yes, for example, you mean about material in like also thermal masses. If you influence the thermal mass, of course, it will actually energy system. And for example, let's say if we have a water-based heating system and we have electric-based heating system, because in Norway we have a lot of direct electric heating system, and in majority of countries, heating is water-based heating system. So when you have water-based heating system, you should be more resilient because you have a thermal mass inside the pipes. So this will help you to be more resilient. But for some countries, is like not the best option for efficiency. Sometimes because it depends on your heating system and also the type of energy resources you have. So this is just like one of examples.
Yes, I understand. Thank you.
Yeah, you're welcome. So that's why it was important when we define resilience we talk about the building or building and energy system or a building energy system and renewables at the same time. Because it depends, the most important to make framework and a clear framework to what we are talking about. Yes. Okay, so I will be happy if you have more questions. I leave this floor for Zara. Now you finishing this session, maybe? We don't hear you. You are muted.
Yes, thank you. Actually, we're gonna take a shot with you for this session, and then we have a quarter minute for break time, and then I'm gonna be ready for a start about the presentation of thermal comfort basics and actually analysis of this. Yes.
Yeah.